Good morning, one and all. Myself, Dr. Amjad, working as Associate Professor in Department of ECE, Cheap Polarity Engineering College. I would like to give demonstration on UJT as relaxation oscillator, which is one of the experiment in the electronic devices and circuits lab. So coming to the UJT relaxation oscillator, the main aim of this relaxation oscillator is to find the frequency of the oscillator. And the components that we are going to use is UJT 2646 and DC power supply 0 to 12 volts, CRO, resistors 100K and capacitor 0.1 microfarad. Here we are going to use. Coming to the circuit diagram, so this is the VCC, DC supply is 12 volts and the resistor is 100K I have taken. The capacitor value is 0.1 microfarad and here the resistor R2 value is 1 kilo ohms and the resistor R1 value is 560 ohms. Coming to the working of UJT as a relaxation oscillator. So first here we are going to provide the DC supply 12 volts. So through this DC voltage the capacitor starts charging through the resistor R. So as the capacitor here, if you observe the waveforms of the capacitor, here the waveforms are, so the capacitor starts charging and it reaches up to a maximum value. This maximum value is called the peak value. So when this capacitor reaches the maximum value, the UJT gets into on state. UJT gets into on state. After that, the capacitor starts discharging through the resistor R1. Through the resistor R1. Here the discharging is given. The discharging of the capacitor is up to the, so it reaches the minimum voltage. So complete discharge, it reaches the minimum voltage. That minimum voltage is known as the valley voltage. When the capacitor reaches this minimum voltage, the UJT gets into off state. The time period for charging is from 0 to T1. The UJT time period, discharging time period is more and the discharging time period is less. It is from T1 to T2. T1 to T2. So during the charging of the capacitor, the UJT will be in off condition, and when it is discharging here, when it is discharging in this time interval, it will be in on state. Now, so the output, this is the first waveform, represents the output across the capacitor. And when we consider the output across the resistor R1, VB1, so this is the output waveform that we are going to get. That is nothing but the positive spikes we are going to get here. So these positive spikes we are going to use in triggering of the devices like SCR, silicon control rectifier. So in these positive spikes, if you observe, so during the discharging time, when the UJT is in on condition, we are going to get the positive spike. And when we take the output across the resistor R2, so here we will be getting the negative spikes. So these negative spikes are used in triggering of the some of the electronic devices. Coming to the theoretical calculation for finding out the frequency of the relaxation oscillator, I have considered the values as R equals to 100 kilo ohms and the capacitor C equals to 0.1 microfarad. The intrinsic standoff ratio value I am going to consider as 0.35. So this can be calculated from the internal base resistances of the UJT. And to calculate the time period, the total time period of the waveform, we are going to consider T equals to RC natural logarithm of 1 by 1 minus eta. So if we substitute the values, R equals to 100 kilo ohms, 100 into 10 power 3 and C equals to 0.1 into 10 power minus 6 natural logarithm of 1 by 1 minus 0.35. So then we are going to get here. So 0.1 into 0.6 is 10 to the power of minus 7 into and 10 square into 10 cube is 10 to the power of 5 natural logarithm of 1 by 0.65. If we simplify this, the total time period here we are going to get is 4.3 millisecond. So the frequency is nothing but the reciprocal of the time period. So if we substitute in this, the theoretical frequency value that we are going to get is 232 hertz. So by varying the value of R, we can change the frequency of oscillation of UJT. So coming to the circuit diagram of the UJT as a relaxation oscillator, if you observe, so this is R1, R resistance R equals to 100 kilo ohms, and the capacitor which I have chosen is 0.1 microfarad. 0.1 microfarad, this is the capacitor, and this resistance is R2 that equals to 1 kilo ohms, and this resistance is R1 560 ohms. Coming to the UJT transistor, this terminal is emitter terminal, and the above this terminal is the base 2 terminal, and the below terminal is the base 1 terminal. So base 1 terminal is connected to R1 resistance, base 2 terminal is connected to R2 resistance, and here R resistance is connected to the emitter, and the capacitor is connected to the emitter. Coming to the connections here, so here we want to provide DC supply of 12 volts. Here we are going to take the regulated DC power supply. So and another equipment which we are going to use the cathode ray oscilloscope in order to observe the output waveforms. So while coming to the connections, this is the DC supply here. We are going to provide these two wires, we are going to connect to the DC supply. So this is plus 12 volts, and the black terminal is grounded, and here coming to the CRO probes, here I am going to connect the CRO probe to the channel 1 here, and the output we can measure at 3 points. The first one is the output is at the capacitor, and we can measure the output at the base terminal B1, and the output can be measured at the base terminal B2. And now first I am going to take the output across the capacitor. Here I am going to connect the CRO probe, and this is ground connection, and this is ground connection, and here we will be having the power supply switch. Please on the power supply switch, and this is the output waveform that we are going to observe across the capacitor, the output waveform across the capacitor. So here it shows the charging of the capacitor, and this is the discharging of the capacitor. Here we are going to calculate what is the value voltage from this zero reference value. So if we observe here, so it is from 2.2 into 2, that is 2.4 volts. The value voltage is here. If we observe in this waveform, we are going to calculate the value voltage from the zero reference level. From this zero reference level, I am going to calculate what is the value voltage. So here if I observe from 0, it is going to cover 1 unit, 1.2 into 2. 1.2 into 2 is, it is 2.4 volts. This is 2.4 volts. The value voltage is 2.4 volts. And now we can calculate the amplitude of this signal. So the amplitude of this signal is 2 point from here 1 unit plus 1 unit, 2.2 into 2, that is 2.2 into 2, it is 4.4 volts. 4.4 volts. So the peak voltage is 2.4 plus 4.4, it is 6.8 volts. The peak voltage will be 6.8 volts. So from this voltage onwards, the UJT gets into on state. The UJT gets into on state up to this value voltage 2.4 volts. Again thereafter the cycle repeats, charging of the capacitor, UJT will be in off state, and again discharging. While discharging, the UJT will be in on state, and here we'll get the positive spikes at the resistor R1 and negative spikes at the resistor R2. And coming to the time period here, the time period is, so it is going to cover 1 unit, 1 plus 1, 2.8. 2.8 into, here we have to multiply with times per division. So that is T equals to 2.8 into 2 millisecond, that equals to 5.6 milliseconds. And to find out the practical frequency, F equals to 1 by T, that equals to 1 by 5.6 into 10 power minus 3. So here F equals to 1 by T, so that equals to 1 divided by 5.6, the value is 0.178 into 10 to the power of 3. The frequency is F equals to 178 Hertz, and this is the practical frequency. The theoretical frequency is 232 Hertz and the practical frequency is 178 Hertz. So we can vary the frequency by varying the value of resistor R to get the required frequency for the oscillation of the circuit. So these are the theoretical calculations, and next is we can connect the output at the VB1. So here we are going to get the positive spikes. So these positive spikes we are going to get when the UJT is in on period. And we can take the output across the resistor R2. So in this case we are going to get take the output across the resistor R2. So here in this case we are going to get the negative spikes. So these negative spikes we can use in triggering of some of the electronic devices and circuits. Thank you very much.